Hello, welcome to lesson 12. In this lesson, we are going to look at calculations on refraction, further calculations on refraction. Let's see. We have here the question, number 1. A ray of light in air makes an angle of incidence 60 degrees with a normal to the glass surface of refractive index 1.5. What is the angle of refraction? Let's see this. So we have this diagram which can represent what we are talking about. So this is the normal, and this is angle of incidence is 90, sorry, is 60, and the angle of refraction is RG. So we are moving from air to glass, so we can apply Snell's law there. So applying Snell's law, you have n air sine I air is equal to n glass sine I glass. So, but what is sine I air, which is 60, and what is sine I glass? It is going to be RG. And then n air is 1, and then n glass is 1.5. So we shall substitute that in that relation. So after substituting, we shall remain with RG that we need. This is a subscript. R subscript G is what we shall be needing. So we shall make that the subject by dividing through by 1.5. Divide through by 1.5. When we divide through, we shall get this. So we know that sine of 60 is 0.866. So we shall get our sine RG and make it the subject, and then get RG as the sine arc of 0.866 divided by 1.5, and that will be 0.5773. So sine of RG is going to be this, and therefore RG is going to be sine arc of 0.5773, which will give us an angle of 35.3 degrees. So the angle of refraction is 35.3 degrees. Let's look at the second example. Monochromatic light, monochromatic beam of light is incident at 60 degrees on a water glass interface of refractive index 1.33 and 1.5 respectively, as shown. Now here, purely we need to use the relation n sine I is equal to a constant, because we can't just use n is equal to sine I over sine R, since we are moving from water to glass. We are not moving from air to glass, so purely we have to use the relation in this case. So the question here is calculate the angle of refraction R. So here we are going to use the relation for Snell's law, and that is NW sine IW is equal to n glass sine I glass. So what I was talking about here, we can't use just Snell's law. N is equal to sine I over sine R. That one will apply as long as you are moving from air to glass or air to any other medium. But since you are moving from water, purely this is the relation you have to use, that is for n sine I is equal to a constant. So when we replace the refractive index of water is 1.33, the one for glass is 1.5, and then sine IW is the angle of incidence here in the water, which is 60, and then sine IG is this R here. So we shall replace that. When we replace, we make sine R the subject, make sine R the subject by dividing through by 1.5, and we shall get the arc sine of 1.33 times sine of 60 divided by 1.5. When we get the arc sine, we get our R as 50.2 degrees. So here you just use your calculator and come up with this. Let's look at the next example. A monochromatic ray of light is incident from a liquid onto the upper surface of a transparent glass as shown. So this is it. The question here is, given that the speed of light in the liquid and glass is 2.4 times 10 to the power 8 meters per second and 1.92 times 10 to the power 8 meters per second respectively, find the angle of refraction. So this time round, I've not given us the refractive index of the two media, but I've given us the speed in the different media. So what you're going to do is you're going to use Snell's law, and we know that this is N liquid sine I liquid is equal to N glass sine I glass. Then we shall replace. This time round, we know that the refractive index in any given medium is defined as the speed of light in a vacuum, or the speed of light in that medium. So with this one, we shall replace NL is going to be C over VL. And then here we shall put 60 for IL, and then we shall put here also C over N V glass from the definition of refractive index. And then we shall also replace this one with R, sine R. So this will be sine R. So that's what you're going to have. So after getting that, now we are going to replace for VL. VL is 2.4 times 10 to the power 8 meters per second. And then this one, VG, is 1.92 times 10 to the power 8 meters per second. So we replace that here. And then the speed of sound in, the speed of light in a vacuum, we know the speed of light in a vacuum is 3.0 times 10 to the power 8 meters per second. So we replace that and then make sine R the subject. So if we make sine R the subject and replace for this and that, we shall have this, divide this by that and multiply by sine of R using a calculator. We can clearly get that value, and then they get the sine of that value, which will give us R as 43.90. Let's look at question 4. A small fish is 3.0 meters below the surface of a pond and 2.5 meters from the bank. A man 2.0 meters tall stands 4 meters from the pond. Assuming that the sides of the pond are vertical, calculate the distance the man should move towards the edge of the pond before movement becomes visible to the fish. So we know that the pond can be like that, quite oval shaped. The cross section may be oval, but here they've specified that the edge must be vertical. The edge of the pond must be vertical, so we shall have a vertical edge. So this is how the diagram will look like: a vertical edge, like that. This edge is vertical. So if these sides are vertical, as I've said, it means that now we can deal with this as a normal. This will be like a normal. So if this fish is 2.5 meters from the edge of, or from the bank of the river, or sorry, the bank of this pond, 2.5 meters from the bank of the pond, and then the eye will be 3.0 meters. So we are concentrating on the eye because it's the eye which is going to see. So you're assuming that the eye is going to be 3.0 meters. So the distance here is 2.5 and this is 3. Now we are going to draw a ray to the edge here because we want to get the minimum distance. So that the eye can, so that this man can just be seen. So we shall draw this ray to the edge here, because you can of course draw it somewhere here and then draw, but what we want is, since we want the distance that the man should move towards the edge, so that before the man becomes visible, the best is to draw it through the edge here. So we shall draw it through the edge, and then when it reaches here, remember this is water, it is going to refract. And when it refracts, we are moving from water to air, so it will refract. And when it refracts, it will be able to see the man. Now, for him to see the man will be 2 meters tall. But remember that this man is at a distance of 4.0 meters. So we shall assume the man is at this point. This is where the man is, at 4.0 meters. But for him to move, he has to move through a distance of 4 minus this other distance, d. Let's call this distance d. So he has to move through a distance 4 minus d in order to be here where he can be seen by this fish. So we are going to let this one be d, and then now what we need is to get this distance d. So how do we get that distance d? The angle of incidence is I, the angle of refraction is r. So we need to first get this I here. How do we get the I? We know the distance from here up to here is 2.5. The distance from down here, that is from the I. We are going to neglect this other distance. We are mainly going to concentrate on the I. The distance from the I up to up here, where the water level stops, is going to be 3.0. So for us to get this I, we are going to use tan. So tan of I is equal to opposite, which is 2.5, divided by adjacent, which is 3.0. So we can get our I as 39.81 degrees. Using your calculator, you can get that. After getting that, we need to get the R. So we shall use Snell's law to get the R. So we shall have our N water sine I is equal to N air sine R. So that we get that R. When we replace this, we know that this one is 1.33, and then we know this one is this 39.81, and then we know air is 1, and then we shall get our R here. So we shall make sine R the subject, and then multiply this one using a calculator, and then we shall get our R by getting the sine arc of this value here, which will give us 58.4 degrees. After getting that, we need to get now the theta, so by getting 90 minus theta, because this is a normal. So it's going to be 90 minus theta, which is 90 minus r to get the theta, and so it is going to be 90 minus 58.4 degrees, which will give us 31.6 degrees. So after getting this theta, we can now get d using still tan. So tan of theta is going to be opposite, which is 2, divided by adjacent, which is d. So tan of 31.6 is going to be equal to 2 over d. And then we shall make d the subject. If I cross multiply, d is going to be 2 over tan of 31.6 degrees. And therefore we shall get our d as 3.2 meters. So after getting that d as 3.2 meters, remember we want to get the distance that this man must move from where he was up to that point where he will be seen, by the fish. So it means that this man will have to move 4 minus d meters, which is going to be 3.2 minus, 4 minus 3.2, which will give us 0.8 meters. Let's look at the last example here. Monochromatic light incident on a block of a material placed in a vacuum is refracted through an angle theta if the block has a refractive index n and is of thickness t. Show that light takes time of nt sec theta over c to emerge from the block. So we are going to have this glass block. So the light is moving from air to glass at an angle of incidence I, and I've talked of the angle of refraction being theta. So we shall put our theta here. And then the thickness is t. The refractive index of this glass is n. So we are moving from air to glass. So we shall need to get the time for it to move from O to B. That's the time needed. But remember, for you to get that time, we can get it by getting first the distance and then the speed. If we can get the speed in this glass and then the distance OB, we can get the time taken to move from O to B. So first of all, let us get that distance OB. Let us get that distance OB. How do we get that distance OB? Remember, we have this thickness, which is the distance from here up to here, and that is T. and then we want this, so that means that it is adjacent and hypotenuse, which is cos. So cos of theta is equal to T divided by OB, and so OB is going to be the distance OB is going to be T divided by cos theta, because this one will move the other side, because this cos was here and OB was down here. So if I take the OB the other side, the cos will come here. So it will be T divided by cos theta, which will give us T sec theta, because we know that 1 over cos is sec theta. 1 over cos theta is sec theta. So we have that OB, the distance OB. Now what we need is to get the speed. So the speed is going to be distance over time. And therefore, we shall get, remember our distance, we know it is T sec theta. The time is what we need. So we shall make time the subject, and we shall have the distance OB divided by the speed, which is V. So the speed in glass, we are calling it V. And we know that OB is T sec theta divided by V. Now what we need is this V here, to replace this V in terms of N, and C. That's what we need. So remember that V can be got from N is equal to C over V, because we say that the refractive index is given as the speed of light in a vacuum over the speed of light in a medium. So N can be given as C over V. So if N is C over V, it means that V is C over N. So we are going to replace C over N here. And if we replace that, we shall be in position to get T sec theta over C over N. And therefore this N will go up. And then we shall have N T sec theta over C as the time taken. Yeah, thank you for attending this lesson. In the next lesson, we are going to look at sidewise displacement, and then we shall also look at how to determine the refractive index of a material.